Okay, I want to continue with the example we started in the last video, but before I do that, I need to acknowledge a mistake I made and correct it. When I was trying to find the slant asymptote, I said correctly that this was a division problem and we needed to divide. And then I copied it wrong. I inadvertently divided by x minus 1 instead of x plus 1. And so that meant that I actually got the wrong value for the slant asymptote. The correct slant asymptote should be x minus 1. In the last video, I had written as x plus 1. So I've gone back and I put a little note on that video, so hopefully that appears at the right time to say, hey, this is wrong. But I wanted to let you know I've corrected that now. If we actually divide by x plus 1, I just miscopied it, we get x minus 1. So I've redrawn the slant asymptote here, like so. We had a vertical asymptote at 1. And we had taken a look at our first derivative and determined that we had a maximum value at -2, -4, and a minimum value at 0, 0 at the origin. Okay. So this is where we would have left off in the last video had I done things correctly. Okay. And I wanted to now take a look at concavity. So we're taking a look now at the second derivative. So that's going to again be quotient rule. So it's going to be low, x plus 1 squared, d high, the derivative of the top will be 2x plus 2, minus high, x squared plus 2x, d low. Now that's going to be chain rule. I've got x plus 1 squared, so I'm going to get 2 times x plus 1 times the derivative of x plus 1, but that's just 1. Okay. So there's my low d high minus high d low. Square the bottom, so x plus 1 squared gives me x plus 1 to the 4th, and away we go. Okay, so I want to simplify this. I think what I definitely want to do is try to do some factoring if I can. Okay, so notice here there are 2 factors of x plus 1, and there's an x plus 1 right there. Also, there's a 2 here. And I could, if I wanted to, write this as 2 times x plus 1. So it looks like I can factor out a 2 and an x plus 1 from the top. Now when I do that, let's just say I took this one out, then I'm still left with these 2. So I've still got x plus 1 squared. I factored out these 2, so I'm just going to distribute the negative here. That's going to become minus x squared minus 2x. And then that's all over x plus 1 to the 4th. Okay. Let's go ahead and simplify a little bit further. Now if I want, I can cancel one factor of x plus 1. So I'm going to have, let's come over here, 2 times x plus 1 squared would be x squared plus 2x plus 1 minus x squared minus 2x all over x plus 1 cubed. Now that's awfully nice because the x squared and the minus x squared cancel, the 2x and the minus 2x cancel. I'm left with just 2 times 1, which is 2 over x plus 1 cubed. Okay. Now, that is always defined on our domain. Obviously, it's not defined at -1, but that's not in the domain of our function. So, I know I'm not going to have any points of inflection here because there's no point in the domain where this could possibly change sign. But I do still need to check for the concavity because I've certainly seen that I can have different types of concavity on one side of the asymptote than the other. So I'm going to create my number line for f double prime, but the only number I'm marking off on there is -1, and I'm just going to make a note that that's a vertical asymptote so that even if the concavity changes, I don't have a point of inflection there. Okay. So, if I pick a number to the left of -1, I'm thinking 0. I'm thinking of 0 as a number to the right of -1. To the left of -1, I'm thinking maybe a -2. Okay. Now obviously the 2 is positive. Negative 2 plus 1 would be negative, and I'm cubing it so it stays negative. Okay. To the right of negative 1, I can plug in 0. That's going to be 2 over 1 cubed. That's going to be positive. So we're concave down and then concave up. But again, no point of inflection because there's no point there. There's a vertical asymptote there. So we are ready to play Connect the Dots. Okay. Let's see. So the asymptote sort of divides the graph up into 2 pieces. So to the left of that, I've got to come up and then down, staying concave down. So I know I start out close to this slant asymptote. So I'm following that. That gives me my end behavior as I go far to the left. We come up to this maximum and then come back down. To the right, we're going down and then up, so I better start up high, come down to that minimum value, and then go up, making sure that I keep that concavity as being concave up. So I like to do a quick check. Did I go up, down, up? I did. Was I concave down and then concave up? Yes. Because it's very easy when you play Connect the Dots to just inadvertently change something as you're trying to get the entire graph drawn. Okay. One word of caution. Sometimes people ask, what should be over here? The answer is absolutely nothing. Okay. There is nothing over here because the domain does go infinitely far to the left, but as we go to the left, we're going down. We've got stuff down here. If I were to draw anything up here, my function would now fail the vertical line test. So a vertical asymptote, I can say, oh, let's look at what happens to the left of it and to the right of it. But with a slant asymptote, I do not want to think of what happens to the left of it and what happens to the right of it, because I can easily, if I have something both to the left and to the right, they could end up above each other and I could fail the vertical line test. So don't think of a slant asymptote as doing anything other than giving you the end behavior as you go really far to the right and really far to the left.